Okay, we are going to practice graphing polynomial functions. So the first thing that we just need to mention is that polynomial functions are smooth and continuous. So that means they don't have any points like this. Okay, that means, so smooth means they're nice and like all the curves are curvy, right? No points. So this is smooth, this is not. Continuous means you can draw the whole thing without picking up your pencil. So for example, this function, there's a big jump, right? This is not continuous. So these two functions might be graphs of polynomials. These could not, because this is not smooth and this is not continuous. All right, so when we draw graphs of polynomials, we always draw them like this, nice smooth curves and as continuous functions. Okay, so we've talked a lot about behavior of polynomials, like end behavior. We've talked about symmetry. We've talked about y-intercepts and x-intercepts. We've talked about turning points. There's one more thing we need to talk about before we're ready to start graphing polynomials. So this is at x-intercepts. Okay, so all of these are three kinds of x-intercepts. Here, the graph crosses the x-intercept, the x-axis. Here, the graph touches the x-axis. And here, it crosses it, but it's like a little bit flattened out, right? So here's what we need to know. I guess some of this is covered up. So if a polynomial contains a factor of this form, there's going to be an x-intercept there, right, at value h. And the behavior is determined by the power of that factor. And then we call that the multiplicity of that factor, or the multiplicity of that zero. Okay, so if the multiplicity is even, like 2 or 4 or 6, the graph touches but does not cross the x-axis. And the higher that multiplicity is, the flatter it gets. Do you remember in the last section, we looked at some graphs that had higher even powers and their graphs got flatter and flatter. Okay, so if it touches but doesn't cross, it's even. And if it crosses, it's odd. Okay, so like these are both odd, right? But this one just crosses it directly. This one kind of like flattens out a little bit, and like p to the 5th or p to the 7th would be more and more flat. Okay, but they still just cross at that one point. So the main thing is if it's even or if it's odd, if it touches or crosses the x-axis. All right, so let's look at this graph and identify the zeros and their possible multiplicities. So it looks like there's a 0 here at -3, and the graph touches but doesn't cross there. So that would be multiplicity 2. How about right here? Well, it just crosses the graph right there at -1. So this would have multiplicity 1. How about over here? It crosses, but it's a little bit flat. That probably is at x equals 4. There's a 0 of multiplicity 3, right? So 3 plus 2 plus 1, or if we add all the powers together, that gives us 6. This would be a polynomial of degree 6, because this 0 is multiplicity 3, 2, 1, and 2, right? So we add those together, we get something of degree 6, or maybe greater, right? Sometimes, we'll get into that, but sometimes there could be like non-real zeros or something that make it have a higher degree, but it has a degree at least 6. All right, so what if we wanted to actually write this formula? All right, so here's the steps. Identify the x-intercepts and find the factors of the polynomial. So these are going to have factors -3, 2, and 5. Examine the behavior to determine the multiplicity. Find the polynomial of least degree containing all the factors, and use any other point on the graph, like maybe the y-intercept, to determine the stretch factor. So let's do that. We have at -3, 2, and 5, we have x-intercepts. So here we write those as zeros, x plus 3, x minus 2, x minus 5. And then we look at how it crosses, right? This looks like it has multiplicity 1. So there's a 1 on that 0. This looks like it has multiplicity 2 because it touches but doesn't cross at 2. So we make that exponent 2. Here at -3, that looks like it just crosses, so it has exponent 1. So our graph is going to have, or our function is going to have this form. So we've done steps 1, 2, and 3. Now we need to figure out what this a is. So we choose any other point. This one looks nice and convenient, right? If x is 0 and y is -2, we say f of 0 is a times this times this times this. Right? We figure out what all of those are. And f at 0 is -2, right? That's why we chose it, because it was a nice convenient point. And now we just solve for a. A is 1 over 30. And so now we can write the equation, put that in for a. Right? So those are the steps. We find the zeros. And we can also ask ourselves, I guess this doesn't mention it, but let's look at the end behavior here. Does this make sense? This was a 6, if we were going to multiply this out, this would be a 1, 2, 3, 4th degree polynomial. And it goes up on both ends like a quadratic. And yeah, so this makes sense that this is positive, right? It's a positive coefficient for a 4th degree polynomial. The end behavior makes sense. It's going up on both sides. All right, what if we want to go the other way? We want to graph polynomial functions. All right, so let's look at these steps. Find the intercepts. Check for symmetry. So we talked about if it has origin symmetry or if it has y-axis symmetry, if it's an even or odd function. That might help us. Use the multiplicities of zeros to determine the behavior at the x-intercepts. Determine the end behavior. Use the end behavior and the behavior at the intercepts to sketch a graph. And then you check yourself. Ensure that the number of turning points does not exceed 1 less than the degree of the polynomial. And then you can always use technology to check your graph. Okay, so let's just practice doing that on a few different problems. So let's go here. All right, here's our graph, or here's our function. F of x equals -2 x plus 3 squared times x minus 5. So let's make our axis 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, first thing, let's think about end behavior. What's going to happen here? This is, what degree is this polynomial? If we multiplied everything out, it's going to be a 3rd degree polynomial, right? We can just add the zeros of those two terms. The 3rd degree polynomial, so it's going to be like x cubed, right? So up on one side, down on the other, and there's a negative coefficient out front. So x cubed would go like this. So this is going to be reflected. So it's going to go up on this side and down on that side. That's going to be the end behavior. Okay. All right, now let's look. Is this going to have any symmetry? I don't think so. If we multiply this out, it's going to be cubic, but it has this coefficient. I don't think this is going to have any symmetry, right? It's not going to be obviously even or odd. All right, how about intercepts? What's the y-intercept? Well, f of 0 is -2 times 3 squared times -5. So -2 times 9 times -5. Oh man, I didn't make my axes big enough at all. It's going to be at 90. Okay. Woo, so it's going to go way up. Did I do that right? Yeah, I did, unfortunately. Okay, this is an interesting example. All right, so maybe these are in tens. It's going to cross it way up here. Where are x-intercepts? They're going to be at -3 and 5. And what's going to happen? Here at -3, it's going to just touch, right? Turn and touch. And at 5, it's going to cross, because this has multiplicity 2, and this has multiplicity 1. So this is the kind of graph I'm looking for. You don't have to plug in a million points. We're going to start up here, touch. It's going to cross way up there at 90. And then it's going to come down like that. Okay? So we found end behavior. We found the zeros and the behavior of those zeros. And then we kind of connected them in a smooth way. and ones that I give you on the test, I'll be more careful, and they will not have like y-intercepts of 90. Okay, so they'll fit on the graph. Let's see if they give us what this graph looks like. Yeah, so they did graph this, and they used proper axes, and I didn't look at that. But here's what their graph looks like. It looks a lot like ours, right? Where's ours? Theirs looks nicer, but it starts up, touches, crosses up at 90, and then crosses the graph at 5. Okay, so yeah, let's try another one. Okay, once again, I'm just going blind here. Let's do this one. X plus 3 squared times x minus 2. All right, let's draw a graph. All right, let's look end behavior. This is going to be cubic. So you could obviously pause this video and see if you can graph this. It's going to be cubic, positive coefficient. So it's going to go up over here and down over here, right? Because if we add these exponents, we get 3. So it's an odd degree polynomial, and with a positive leading coefficient. So it's going to go up over here, down over here. There's a x-intercept at -3, where it's going to touch and turn. And there's one at 2 where it's going to cross. And let's see, f of 0 is 3 squared times -2. So -18. So once again, I don't know, somewhere way down here. All right, so our graph's going to look something like touch and turn, cross at -18, and then cross at 1. Okay, let's find one with, all of these have odd multiplicity. Okay, let's do one more. Let's do the 47. So minus 3x, n of x is minus 3x times x plus 2 times x minus 4. Okay, let's graph our axes. End behavior, let's see, this is going to be degree 3, right? 1 plus 1 plus 1. So it's going to be like x cubed, except it has a negative exponent out front. So it's going to go down over here and up over here. And let's see, the y-intercept, f of 0, is -3 times 0 times 2 times -4. So it's going to be 0. Okay, well, that's nice. It's actually on my axis this time, so hooray for that. So x-intercepts are going to be at x equals 0, already got it, at -2, and at +4. And it's going to cross, all of those have multiplicity 1. So it's going to cross the axis at each of those points. So we're going to start up here, go down, and like this. And let's just check, we have 2 turning points here, which makes sense because this is a 3rd degree polynomial, so we can have at most 2 turning points, and that's what we've got. All right, so those are some examples of how to graph polynomials using all these different pieces of information. The biggest piece, the 2 important things you can't ever forget are thinking about the end behavior and the multiplicity of the zeros. All right, those are going to be the key things to getting your polynomial graph correct. The homework will give you plenty of practice.